Okay, so this way is to calculate W, mass flow rate. Mass flow rate can be calculated based on X and film profile. Okay, see the equation. WL has to do with the film profile, or film profile is HLTB, and the hole up inside the slug body, and X value. Okay, so when we calculate film profile, if we have the film length too long, WL that is calculated by this way is not going to match the given WL. Okay, we want to stop film profile calculation when WL calculated from the film profile calculation match with the given WL. For a certain flow condition, we know mass flow rate, right? So we stopped film profile calculation when WL match with your input WL. Okay?
So you said the mass flow rate is not the same everything.
X,
No, mass flow rate.
WL, this total WL, everything for the whole slug unit.
It's like at the inlet.
And it is the same as at the inlet. This WL is WL at the inlet.
And slug.
So we have to use this formula. It's not about the same everywhere. You get film profile, you get slug body, you account for every location. Then you get the WL. Let's take a look at the derivation. Why do I say it's not the same everywhere? If there is no X, let's say you have elongated bubble flow. Okay. Let's say you have elongated bubble flow. Velocity profile, velocity everywhere in the liquid phase are the same and the same as VTB. You see it's like bubble floating. Everything moves at the same speed. Okay. If we have that, you don't have X, right? How do we know mass flow rate? Mass flow rate for elongated bubble flow case is for one location is VL. If velocity are the same, actually we cannot have velocity the same everywhere. For the case of slug flow, okay, let's start with elongated bubble flow. For elongated bubble flow, we don't have X. Okay. What we do is we take a picture, and then divide it by the elongated bubble flow period. Okay. When you take a picture, you want to know how much volume is inside or how much mass is inside. Amount of mass is inside is HLRS, which is hole up, right? Hole up in the slug body, multiplied by AP is the cross-section area for liquid phase in the slug body. Good. Multiplied by LS, slug length. So this gives us the volume of liquid in the slug body. Volume of liquid in the slug body is AHL. Volume multiplied by density, we get mass that is in the slug body. Okay. This integration is to get mass in the film. Mass in the film is rho dV. Okay. Integration of rho dV, and V is not velocity but volume. Rho d volume. The volume is AP, HLTB, this is AL, cross-section area that is liquid. Okay, this is cross-section area that is liquid. Multiplied by D length, this will give us dV. HDL is the volume. Okay, d volume. So rho d volume, do the integration, this gives us mass in the film zone. And if we know that this whole mass move, take TU, which is the slug unit period, take TU time to repeat itself. So we know that within that capital T sub U, it repeats itself. So we know that this amount of mass move will be replaced every TU. Okay, this amount of mass will be replaced every TU. So mass flow rate is that mass divided by TU. Yes.
Because our film length really goes to zero.
Film length
LF.
L sub F. It's not zero. It's not zero.
Because your boundary is what I'm saying. You will actually get to zero. You will get to zero, and you know overestimate.
LF is length in this direction. Film length. Film length is not zero. What are you talking about? Are you talking about the height?
No, I think it's counted in this yeah. It's just a range to measure an exact equal to a field. That's all that is.
Okay, let's take a look without integration. Without integration, let's say remove the integration sign. Oh, how do I remove that? Okay. Remove the integration sign. And we say hold up is constant. So this L, this DL change to LF, right? So LF multiplied by AL give us volume in the film. Multiplied by density give us mass in the film. Just that. If hold up is constant, we can do this, right? If it is not constant, we have to do the integration. What are you doing? What's that? Put it in the trash bin, okay?
It's not mine.
Oh, okay, you're stepping on it. So, if it is constant, we can do multiplication. If it is not, we do the integration. And length of the film. If your length of the film approach zero, this means it's not slug flow anymore. It's become this bubble flow. But it's not this. We need X. Yes.
So for a steady state case, this WL is going to stay the same for all T every time.
For TU, WL.
For each snapshot, for this snapshot, it's going to repeat. It's going to repeat for different times.
It's going to repeat. Yes.
So for steady state, it's going to be the same. For transient, it's going to change, right?
It's going to. We can say steady state means nothing change with time. But slug flow, it always change with time.
So
We don't have steady state. We can have pseudo steady state.
I want to ask
Periodically repeated itself.
how applicable here if you want to actually do it for your experiment.
This equation correct 100%. No assumption in
But
this.
for different T, as you said, it might change. So
We cannot really this equation is not to calculate local WL. This equation is to calculate overall WL. Whole mass of liquid per unit time, which is equal to whole mass of liquid per unit time at the inlet.
an inlet.
Yes. So we cannot really do for just one location. We do for the whole slug unit. Okay. We do it for the whole slug unit. If there is no shading, you don't need this X term. You just take a picture and you know that it repeats itself at a certain time, right? So you know that by that time it moves this much, so mass per that unit time is like amount of mass that you added in. So it moves and repeats itself at that amount of time. But there's a shading. Shading is this. We have mass come from the slug body to the film. Okay, the flow direction is this. Okay, and there's a mass pickup rotating inside and shed at the back. You see this? So when we use a freezing method, take a snapshot. We don't know what is moving inside, right? Taking a snapshot is the same as we are moving observer. If you move at the speed of Taylor bubble, everything is kind of frozen, stays still, doesn't move. But there is something moving in it, right? So we have to account for that, which is X. Think about this. If we have a lot of shedding going on, so we flow to the right hand side 1 kilogram per second. but we do the shedding of 0.5 kilogram per second. So we move 1 per second, but we move back 0.5 per second. So for the moving observer, you have to do everything which is 1, right? And minus shedding which is 0.5. So that will be your net W. For moving observer, they will see everything stationary, right? And the mass per unit time is total volume multiplied by density divided by time. Minus whatever shedding process happen, or X, pick up and shedding, because this thing kind of flow back. It doesn't move forward with the slug body. If you still recall the example that we talked about on the introduction to slug, we talk about some solid particle which is no slip, right? It moves inside. When we move 1 slug unit, the particle inside doesn't move 1 slug unit, it moves less. So the total mass is not total volume multiplied by density divided by time. It's not just that. Have to minus shedding. Okay? Put here liquid mass flow rate to the right side equal to mass in the control volume divided by Tu minus X. Clear enough? Can you do this for gas? More dear. Wg equal to what? Do you have it in your book? Is it in the book? You have WL, right? What about WG? Is it in the book? No, it's not. So it's a good question to ask when we do closed book or even open book because it's not in the book. So how do you do for WG? Model, what parameter do you have to change? TU stay the same, right? Will you change rho L to rho G? Okay. What about HLS? Will be alpha LLS, right? Whole up. Change from whole up to void fraction, which is 1 minus whole up, right? So integration from 0 to LF, is it stay? Yes, stay the same. Rho L change to rho G. This change to 1 minus that, right? What about X? Are you going to change X to Y? This X is shedding rate for liquid, but you need shedding rate for gas. How do you get shedding rate for gas?
In the formula, we have to change the for gas.
Yes, it is in the formula. So shedding rate for gas. Let's take a look at X. X is VTB minus VS multiplied by HLLS AP rho L. That is X. So shedding rate is calculated based on moving observer, right? The mass, the relative velocity that move past the interface. So for gas, if this is X, let's say XL or just X. For gas, shedding rate will be VTB is the same, right? VS is the same because gas inside move at the same as slug. Gas and liquid move at the same speed. HLLS will change to, yes, 1 minus HLLS. And rho L change to rho G. Then you get pick up and shedding rate for gas phase. Does it make sense? Not really make sense because you forget how we derive X, right? How do you derive X, Raymond? That is the problem. How do you derive X? How do you derive X? Where does this come from? You still remember that? Really? In the moving coordinate, liquid move back at the speed of VTB minus VRTB. And the cross section over that point. Oh, let's take a look at this. Liquid move back at the speed of VTB minus VS. And when we are in the slug body, the cross section area is HLLS multiplied by AP, right? If you look at gas phase, gas move through the slug body, right? In the slug body we have gas, right? And it goes to the gas pocket. So in the slug body, gas move toward the boundary for the moving observer at the speed of VTB minus VS, right? And the cross-section area of gas is what?
With VT, it's different with VL.
For horizontal flow, VLLS and VTLS, they are identical for horizontal flow, and they are equal to Vs and equal to Vm.
It's not in the tailor bubble itself.
Okay, look at this. If you have upward, VGTB is greater than VGLS and VGLS greater than VLLS. This is not in the tailor bubble. This part is in the slack body. For horizontal flow, both of them are the same, equal to Vm and Vs. Okay. Gas in tailor bubble move faster. Okay. But interface move even faster than the gas in the tailor bubble. Okay. So mass that go through this boundary, for moving observer will be relative velocity. Relative velocity is VTB minus Vs multiplied by cross-section area, which is 1 minus HLS multiplied by AP multiplied by rho. Okay, that is pickup rate inside the slack body. Inside the tailor bubble, what do you have? VTB minus VGTB. Yes, VTB minus VGTB multiplied by 1 minus HLTB multiplied by AP multiplied by rho. Very good. You get it? Kind of.
Problem is you can't use that assumption because if your velocity is changing and your pressure is changing inside the tailor bubble, and your density will be changing. So how do you?
Okay, changing density. This model, even Catobania, they assume no changing density in the gas phase, in the gas pocket, no density change. In the gas phase, no density change. In the gas pocket, no density change. Okay, in one slack unit, no density change. Okay. Of course, VGTB change with location. So if you do mass balance at this location, you use VGTB and 1 minus HLTB at that location. If you do it at another location, you have to match VGTB and HLTB at another location. So that X for gas phase is the same throughout for moving observer. Okay, for moving observer, X will be, for gas phase, X will be VTB minus Vs for horizontal flow, multiplied by alpha LLS, or 1 minus HLLS, multiplied by AP, multiplied by rho G. Okay, that's for gas phase. Alright, let's go back. For the case that we are talking about, method 1 is freezing method. You find the equation in your book, right? 3 point what? Arya? Am I disturbing you from your text message? Not quite, okay. 3 point what? In the book? 3.111, okay. Okay, there's another method. Overall balance. Not take a picture, but do the time integration. First method is frozen, right? Freeze it and account for X. So integrate the amount of mass passing through a certain cross-section area from 0 to TU. So we stay with the pipe. Previous one is kind of the method for moving observer. They see everything is stay still. So this time we stay constant with the pipe and do the integration. Okay. WL. So we integrate every mass that moves through a certain cross-section area, right? So if I wait, this is my pipe. If I wait this here, okay, and I have slug body come, and then we have liquid film come. So slug body, when it passes this dashed line, the volume or the mass that passes will be density multiplied by volume, right? Volume that passes will be velocity multiplied by cross-section area. Velocity is Vs, cross-section area is AP HLS, right? So This times this give me mass per unit time, right? Area multiplied by V become volumetric flow rate. Volumetric flow rate multiplied by density become mass flow rate. If I want to know amount of mass, I use mass flow rate multiplied by time, Ts. How long does it take for this arrow to stay inside the slug body zone? So this arrow stay for Ts second. So I multiply by Ts. So that give me mass, right? Okay, next we consider the liquid film part. Liquid film part, the height is not constant. If the height is constant, we can forget about this. Add bar over here. Instead of this dt, we say Tf.
What is the unit of
Second. Not temperature, okay? So let's say height is constant. If height is constant, I use volumetric flow rate. Volumetric flow rate is area multiplied by velocity, right? Area is, okay, and put bar on this. Area is AP multiplied by HLTD. That's area. Multiplied by velocity, which is VLTD bar. Multiplied by density, that give me mass flow rate. Mass flow rate multiplied by time. How long that arrow will stay in the film zone? Ts. So multiply them together, I get mass that pass through that battery. Okay? So total mass divided by Tu, I get mass flow rate. Okay. We cannot neglect the integration sign when VLTB is a function of time. HLTB is a function of time because when I wait at a certain location in pipe, film that pass, sometimes it's thick, sometimes it's thin, right? Sometimes it's fast, sometimes it's slow, based on what location. So that's why we need integration sign. VLTB, how do we get VLTB in terms of time? What do you do? Okay, maybe, do we have it? Okay, let's talk about that later. Douglas Hubbard model used this approach to obtain the relationship between slug length and WL. Okay, and we have equation 3.113. To get from 3.113, we start with this. X equal to X, right? VTB minus VLTB, that's relative velocity multiplied by density and cross-section area that give you mass that move past the battery for moving observer. Okay, which is X. Right hand side is also X. Early on you have VTB equal to 1 plus C multiplied by Vs. Okay, then what do? We cancel rho and rho, AP and AP. Cancel each other. Okay, and HRTB multiply this, you get this term, right? HRTB multiply this, we get this term. Okay. Okay. And the right hand side, VTB minus Vs. VTB minus Vs. I put here C, CS, HRS. Is that right? Okay. C. Yes, that's correct. VTB minus Vs is Vs multiplied by C, right? So I put it here. Vs multiplied by C is this thing. Right, and this part, just move that. Okay, so basically combine this C expression and X equal to X. Do some math, change from left to right, right to left, you get equation 3.113. Arya, you don't have the book, okay. Sweta, what do we do with 3.113? What is that for? Okay, so this means if we know HLTB, so it's a relationship between VLTB and we have to substitute the above equation, yes. And then you get W in terms of several things. So the above equation look like this, right? That's the above equation. And do some math. Divide the whole equation by AP and rho L, AP, rho L. Move it over here. Okay. Inside we have just this much left. VLTB, HLTB. Substitute from previous slide. See this term from this slide? It go in this box. Okay. Put it there. Do some manipulation. We get this equation. Okay. Now this part, the trick here is we have to change from dt to dl. Okay. Change between, because we cannot really integrate it, right? If everything is HLTB is dependent upon length, not time. Okay, so we change from time to length by use this expression. dt equal to VTB dl. Does it make sense? So this is telling us that velocity multiplied by time equal to the length. Length of what? Length that the Taylor bubble move, right? And if we stay at one location, we want that Taylor bubble to move equal to LU, right? Whole LU. So I have TS, which is a time that one location of the pipe will see the slug body, will touch with the slug body, equal to LS divided by VTB. So this is the time that that pipe will see the slug body for one slug unit passing by. Substituted in, I get 3.115. Good? Okay, those you who have book 3.115 is on which page?
97.
You open 97. The exam, last exam will be open book, okay? So you have to practice how to open your book. Okay. What about 3.115? 115 is the same thing. So this time, slug length in terms of VWL. Basically, we do several things and several more things. At the end, I get 3.117. That's not what you want to hear, right? Several things and several more things, and we get 3.117. 3.117 tell us the slug length in terms of WL. Okay, so basically, if we know WL, we put WL in here. If we know VRTBE, we put in here. We know C, we put in here. Put everything here, then we can get slug length. Okay, slug length. So note that this slug length is from mass balance equation, which is correct. It does not need to be 30 diameter. Okay, slug length doesn't need to be 30 diameter. Typically, in most correlation, closure relationship say slug length is 30 diameter. Okay, that's from closure relationship. From your observation, doesn't matter how big the pipe is, doesn't matter how much the viscosity is, which is not true. Okay, so if you want to get the true slug length, this is what it is. Okay, how do we go from 3.115 to 3.117? We will not go through in every line, but there's some trick that you want to know, not to want to. Assumption that you want to know. They assume that HLTB is the same as HLTBE. Once you do this assumption, you don't need to do integration anymore, right? You don't need to do integration anymore. So integration sign is gone and change from DL to LF. Okay. Then substitute L film equal to L unit minus L slug. L unit is VTB minus new Hertz Hz. New is slug frequency. The unit is 1/second. So it will tell you how many slug pass 1 point per second. So if you wait 1 minute, you count 60 slug. So new is what? 1. Okay. Alright? Substitute this in, so it become this part, right? So this part, what do? I rearrange it. So rearrange it, I get 1. That stay the same. This part stay the same. Basically, I think I multiply it in. I multiply this new inside, which is pop up over here. Or that new is here to begin with. That new is frequency. Okay. New is frequency. This from when we change from dl to dt. Okay. So put that new in, and you see this term, the term in the back, this green term. Rearrange it. It's kind of multiply it in. This multiply that. This multiply this. You get this 9. Okay. Rearrange it. The dark green part become that part. Can you do it? But it says doesn't have anything. This is how I did it. The way that you do it doesn't need to be this. The actual question is, can you do it? Okay. I cannot tell you when it is open book. So when you do it, rearrange it. So from this line to this line, see I change from C to 1 plus C. This get changed. So it's like substituting and rearranging. And Vs, I use this equation. VTB minus 1 plus C. Which page number has this? Akin? Which page number has this relationship? Vs equal to VTB over 1 plus C. Which page number? What? 92. Okay. Which equation? Okay. 3.91. Everyone follow that? So put this in, rearrange it. We get this. Note that this equation has the assumption of film height is at equilibrium film height. When you actually do it, you don't need to do that assumption. Okay? You can actually, you don't even need to use this equation, okay? This equation is not needed. No, you don't need this equation. What you have to do is, you have to change just this. That's it. When you change dl equal to vtb dt, or dt equal to dl over vtb, substitute this into your original equation, which is this term, right? dt is what? dl over vtb. Substitute it there. Then from 0 to tf, we integrate from 0 to lf. Right? Then you can do your numerical integration. Okay? And this ts, can we change ts in terms of ls? What is that expression, Maya?
It's LS divided by VTB.
ls divided by tb. So we have, instead of ts, we can say ls divided by vtb, right? ls divided by dtb. So what about film length? 3.117. Does it have film length? Film length is gone somehow. How do we remove the film length? You notice that? How do we remove the film length? Maya? Okay, how do we remove the film length? We use this, right? LU minus LS. And LU is slug frequency, VTB divided by slug frequency, and then LS, right? So everything can be written in terms of slug frequency and LS, right? So this relationship will tell you the relationship between, so TS can be changed to LS over VTB, and LS can be changed in terms of film length, right? LU minus L film, and LU can change in terms of slug frequency. So we are not at what's that model, 1975 or something? We are 2016, right? Our computer is a lot faster. So what you can do is, you can integrate it numerically. Start with this equation. You have the profile. You can check whether your film length is too long or not by integrating directly. And you adjust, you change the film length or something. So this is the relationship. 3.112 is the implicit form of the relationship between film length and mass flow rate already. So this has three things to do with it. So it's mass flow rate, slug body length, slug frequency. Okay, and these two come from calculation. This equation 3.117 and 3.112 is the equation to do the final check. Whether when you do the integration, you have mass balance or not. You can use 3.112 directly. Yes, question.
3.1.7 is derived based on that integral had an assumption.
Assumption
That
H is HE, yes.
So what was the assumption that we could get everything out of the integration?
No assumption. If we do the integration, we don't have to assume that HE equal to HE. We integrate it directly, numerically. Can you integrate it numerically?
Numeric, but
Yes.
they integrated analytically, right?
Yes, they show us how to integrate it analytically.
And there is no assumption, so it's...
The only assumption is this: H equal to HE. So the way that the integration sign is removed by use H equal to HE.
So you're saying this is not accurate and we shouldn't do this, right?
You can use it when you don't have computer. Like if you have just calculator, you do that. If you have computer, use a better way. Okay. Next part is about gas pocket velocity. For gas pocket velocity, you can have mass balance. Same thing, right? But this time is 1 minus HLS. See this is X, kind of X for gas. X divided by AP and rho G. Okay. X for gas in the slug body, X for gas in the telephoto zone. You have this, right? Do some manipulation. We get 3.119. So this is to check if you have gas mass balance or not. So once you solve Doppler-Hubbard ODE, you have to check whether gas balance or not, liquid balance or not. If gas balance, liquid balance, you're fine. Okay. So you can calculate also gas mass flow rate. The equation we just reviewed. Similar to this, but change several terms, and then you have gas mass flow rate, and you can check whether your gas mass flow rate match or not. Everything should match at the same time. If your film length is correct, your slug body length is correct, everything should match at the same time. Calculated gas mass flow rate, calculated volume liquid flow rate should match with the input. Okay. So if you don't have closure relationship, you can adjust film length and slug length, maybe 2 at a time to match those. Use some kind of optimization, but you don't have to do that. Doppler-Hubbard suggests something, and there's a calculation procedure. Okay, we still have 3 minutes. This equation is the equation to calculate mixing zone in front of slug. Okay, I just showed you the equation. The equation is also in the book. This term, head velocity. That term, 3.120. Read it, okay? Whereas that this is mixing length. I don't know, he didn't say anything, it just popped up. There's no derivation for this. Okay? Mixing length. I think they measure it and it's kind of match. If slug moves fast and liquid film moves slow, we get longer LM compared to the case where slug move fast and film move fast. Does it make sense to you? Basically, we try to analyze this equation. If Vs is move fast, film moves slow. Slug body move fast. A lot of Vs, but VTB is slow. So there's a lot of mixing. That's what this equation says. Does it make sense? We don't know. We have to see the lab, but that's what Dr. Hanaba said about mixing length. We don't have the derivation. Yes.
Is there any liquid in the gas pocket?
It can. That model doesn't account for that. The case where you have liquid in slug body is when you have gas phase. If you do it with oil with interfacial tension, if your interfacial tension low enough, in the slug body we have stratified wavy, right? It can have atomization and your bubble can go into the middle. That can happen too, and I have seen that too. Oil film can also have gas in oil film. That model doesn't account for that. You will have to tell me about that, okay? We do the case where oil film doesn't have gas. A little bit, okay? The H model requires two additional input parameters. Double Hubbard requires H LOS and flux frequency, nu Hz, in order to have the model closed. Number of equation the same as number of unknown. Okay, how is still 1229? Calculation procedure. We start with fluid property and known input and inlet. VSL, VST, REST, RESL, WLWG. This can be calculated without doing any more calculation, right? Then we calculate slug frequency from closure relationship. Closure relationship is in the book. We calculate slug frequency from closure relationship. From slug closure relationship, we can calculate VS and so on and so on and so on. We don't have enough time to cover this, but I would like you to read it a little bit so next time we can go faster. Which page number that had this calculation procedure? Tell me and then go home. 98. Okay. 98, 99. Read it, okay? So that is calculation procedure. Is it correct when you tell me? 98, 99? Yes.
If you read this book, it's going to explain why that's when you said LTV, it's not an HLTV, it became HLTV. And that, because of that, we don't need to do the integration.
That's the assumption in double Hubbard.
The screen. Not just copy to the electron